Okay, so this is question 1C. Question 1C asks us to determine the interval of convergence of a given power series. So for the interval of convergence of a power series, we use the ratio test for absolute convergence. Always, that is the test we use. So let's go and apply that test. So we'll call our quantity rho, and that is the limit as our index k tends to infinity of the absolute value of the ratio of successive terms. So on our numerator, we'll have our general term corresponding to index k plus 1. So I rewrite my term, replacing k with k plus 1. Now, be a little bit careful here in the denominator of the term. A very common error that students make is to simply write 4 to the 2k plus 1. In fact, we do need to replace k with k plus 1. So we do need to write 2 outside of k plus 1. So in fact, really we have 2k plus 2. That is a common mistake that students make. Please be careful about that kind of thing. So that's our numerator, and on the denominator we just have our general term corresponding to index k. So now it's simply a matter of simplifying this expression. Let me move over here to the right. So the limit as k tends to infinity. Let me put this all on a single denominator. So let me deal with the 2x minus 3 term first. So on the numerator, we have 2x minus 3 to the k plus 1. On the denominator, 2x minus 3 to the k. And then otherwise, we'll have, going down to our denominator now, 4 to the 2k plus 2. And on the numerator, coming back up here, will be 4 to the 2k. Okay, so let's simplify now. So we have k plus 1 copies of 2x minus 3 and only k copies in the denominator. So that will simplify to just one copy of 2x minus 3 in the numerator. So in the denominator, 4 to the 2k plus 2 is actually equivalent to, let me just use my eraser. So this is equivalent to 4 to the 2k times 4 squared by our exponent rules. Let me just put that here. So now our 4 to the 2k cancels, and I'm left on the denominator with 4 squared, which is of course 16. And of course, k now does not even feature in this quantity, so that is of course equal to 1 on 16 times the absolute value of 2x minus 3. So that's the result of applying the ratio test for absolute convergence. So now to determine the interval of convergence, we need this quantity to be strictly less than 1. So the series converges when this quantity that we calculated is strictly less than 1. The series will diverge when this quantity is strictly greater than 1. We don't know what happens when this quantity is actually equal to 1. Those correspond to the endpoints. We'll check that separately later. Now, for now, let me just massage this expression a little bit, just to enable us to get the interval that we need. So let me take the 16 over to the other side. So in other words, the absolute value of 2x minus 3 must be less than 16. Let me factor out my 2 actually. So x minus 3 on 2 is less than 8. So this gives me a form x minus c, the center, x minus some quantity, x minus c is less than some value. So this is actually the radius of convergence. We weren't explicitly asked for that in the question, we just asked for the interval, but this is the center here of our interval, namely x equals 3/2. So let me just draw a little diagram on the real line as to the interval that's relevant to the convergence of this series. So on the real line, let's say we have 0 somewhere, we've got x equal to 3 on 2 here, let's say. So our interval of convergence extends 8 units either side of the center 3/2. So we've got 8 units in one direction. So this is the boundary of our interval, and we've got 8 units extending in the other direction. So the endpoints of our interval will be 3/2 plus 8. So 3/2 plus 16/2 is 19/2 at one end, and 3/2 minus 16/2 should be minus 13/2. So we know our interval extends from minus 13 on 2 up to 19 on 2. We know that our series converges everywhere inside this interval, and it diverges everywhere outside that interval. What we don't know at this point is what happens at the endpoints themselves. So we know we're talking about this interval from minus 13 on 2 to 19 on 2. We just don't know if we should include these endpoints or not. Should either or both of these brackets at the end be square or not to indicate that the point in question is included. That's what we need to investigate now. So the way to do that is to test the particular series corresponding to each endpoint. So what we're going to do is we're going to substitute x equals minus 13 on 2 firstly, and then later x equals 19 on 2 back into the series itself. So let's do that now. So we're testing our endpoints. Let me start with the leftmost endpoint, x equals minus 13 on 2. We want to know if the series converges at that point or not, to see if it should be included in the interval or not. So at x equals minus 13 on 2, the series is, so what we're going to do is we're going to take our little series and we're going to substitute in for x the value in question, which is minus 13 on 2. So general term now, looks at the sum for k equals 0 to infinity of 2x minus 3. So 2x, so 2 times minus 13 on 2, so that's minus 13, minus 3, all to the k, on 4 to the 2k, so 4 to the 2k is actually 16 to the k, so that is now, let me see, so minus 13 minus 3 is minus 16 to the k, on 16 to the k, So in fact, our general term is minus 1 to the k. So that is the particular series we obtain at that left-hand endpoint. So in other words, this series is going to be it'll start with plus 1 when k equals 0, and then we'll add minus 1, plus 1, minus 1, plus 1 forever. So that will obviously diverge. That never will settle down to any particular value. And we can see that this, in fact, doesn't satisfy the divergence test anyhow. This general term does not vanish in the limit as k becomes infinite. So, in fact, that is a divergent series by the divergence test. So this series diverges, for example, by the divergence test. So far we've established that at this left-hand endpoint, we do not want to include that endpoint. So for sure, this will be a round bracket, an open boundary, an open interval at this end. We do not include that point because the series diverges there. So it's not convergent, it's not included. Let's now examine the right-hand endpoint. So at x equals, So at x equals 19 on 2, the series becomes again, the general term is 2x minus 3 to the k, so 2x, 2 times 19 on 2 is 19, minus 3, all to the k, on 4 to the 2k, which again is equivalent to 16 to the k. So we have 16 to the k on 16 to the k, and that is in fact just 1. So again, that series is just going to look like 1 plus 1 plus 1 plus 1 forever. Clearly that is not going to converge to anything. It's going to get bigger and bigger indefinitely. So this series likewise diverges. And again, we can see that by the divergence test, the general term does not vanish in the limit as k tends to infinity. This series for sure diverges, which we can clearly see. So this also tells us that our right-hand endpoint likewise is not included in the interval of convergence. So again, we do need this round bracket here to indicate that that endpoint is not included in the interval. So this is in fact exactly our interval of convergence. It's an open interval from minus 13 on 2 to 19 on 2. So we'll just write this as our final answer. So thus, the interval of convergence is the open interval from minus 13 on 2 to 19 on 2. All right, so see you for part 1D in a moment.